All right.
Okay.
So welcome everyone. Yeah, we have the pleasure today to host Daniele Malafarina, who is going to talk about the regular black holes from gravitational collapse. Daniele is based at the Nazarbayev University in Astana, in Kazakhstan, and I had the pleasure also to be a postdoc of his a couple of years ago. He got his PhD in Poland, right, with Jerzy under the advisory of Jerzy Kijowski.
Yep.
And then correct me if I'm wrong. What I remember, I'm saying it out of you were in Tata in India, and then in Fudan, and then in Astana, right?
Exactly.
Yeah. The floor is yours. And
thank you. Thank you very much. Thank you, Kostas, for the introduction, and thank you very much for the invitation on this very nice initiative and series of seminars. I'm actually kind of honored to be here because I saw the list of speakers before me, and I feel like a little bit humbled of talking about my things on gravitational collapse after so many interesting talks in the weeks before. And the idea is to talk a little bit how to modify the final stages of collapse in order to produce a regular black hole rather than a black hole with a singularity. So please feel free to interrupt me anytime if you have any questions or anything that is not clear. I will have a part of the talk that is going to be very broad and introductory, talking about the problems. And then towards the end, I want to specialize the whole discussion to two examples that are based on these works that you see here by myself and Bobby Toshmatov in Tashkent, and by myself and Alfio Bonanno and his student Antonio Panasetti in Catania in Italy. These are two works that showcase how you can obtain a regular black hole from gravitational collapse with some simple modifications of GR in the strong curvature regime. The plan is here. I usually don't like having plan of the talk slides, but everybody's doing it, so I felt like, okay, let's do it as well. At beginning is black holes, things that we all know, but still worth mentioning because there's different ways to go about it. And sometimes when you talk about these things with astrophysicists, some things that are pretty obvious to theorists are not so obvious to astrophysicists. So I always feel like it's worth to mention. In terms of mathematics, black holes are characterized just by their mass, angular momentum, and charge. If we're thinking about objects in the universe, we generally believe the charge can be negligible. So we're thinking about only mass and angular momentum. And so it's either Schwarzschild if it's non-rotating, or the Kerr black hole if it is rotating. So the big question is, are those things that we see from astrophysics that we call astrophysical black holes, are they exactly described by the Kerr solution? Are they exactly Kerr, or is there some deviation? So we have lots of evidence from X-ray binaries to quasars to now the image of Sagittarius A star and the black hole in the M87, plus a bunch of gravitational wave detections from merger and in spirals of binary black holes. So are those exactly described by the Kerr solution, or is there some modification? So this is the main question that is basically interesting for astrophysics and interesting for theoreticians on the other side. Because if these things are not Kerr black holes, so what they are they described within general relativity, or are they described by some modifications of GR? So the first thing to keep in mind, that is something that not everybody thinks about, is that we can't tell, even in principle, because a black hole is black by definition. So every signal that we can receive from one of these objects has to come from the vicinity of the horizon. So we never see anything that can actually fundamentally prove that there is a horizon there. We can possibly put some constraints on deviations from the black hole geometry, but we will never be able to say with 100% certainty that that object has a horizon and it's exactly the Kerr spacetime. This may not matter in some sense, because at some point, if there's no way of telling the difference, so okay, let's just call that a black hole and be done with it. But from the point of view of a theoretician like myself, it would be nicer if it was possible to tell the difference and then be able to see, okay, this is, we have some experimental evidence of GR failing and then we need something else. We need something better. So at present, we don't have that. This picture that you see here is a Penrose diagram of collapse to black hole, and there may be photons coming from the boundary of the collapsing object. As the collapsing object gets closer and closer to the horizon, less and less photons reach a faraway observer, so that at a certain point, when you're close enough to the horizon, you will see only a handful of photons reaching you in a lifetime of the universe. And so basically you see nothing, and that's why you see dark. So from the point of view of a theoretician, it would be nicer if modifications to a black hole were visible. We would actually be able to get some evidence. So this is the kind of thing that I'm interested in. And so far, in the past few years, I've been looking at this from 2 points of view. One is objects with horizon. So if there is a horizon, then can we tell if it's exactly Kerr or if there's some modification that maybe make the horizon last for a finite amount of time and so on. Or horizonless objects. There could be objects that are stable configuration that is beyond the neutron star degeneracy pressure, and that they are so compact that still they look dark, but they have a surface. So there is no horizon and there's some objects with the surface. Since we're talking about collapse here and we're talking about black hole, collapse to black holes, I will focus on option number one. That is, yes, let's consider models in which a horizon actually forms. So within this, singularities are generally considered an artifact of the theory. The fact that we're looking at gravity in very strong curvature at very small scales. And so in a regime where most likely general relativity doesn't work. The general picture is usually something like this, where if you go at large curvature and large distances, GR works, and large distances can include the horizon scales, yes? Because a few kilometers may be large enough for the curvature or the size of a supermassive black holes. The curvature is even not that large at those distances. So at horizon scale, we're still at large distances. But if you go at small distances and large curvature, then you may need what people believe to be a theory of quantum gravity that we don't have yet. I say what people believe because there is, okay, let's just put it like this. There is no reason a priori to believe that you have to go from general relativity to quantum gravity. GR in itself doesn't know about H bar in the same way as Newtonian mechanics doesn't know about H bar. So if you take Newton's theory can be valid all the way until you get infinite densities and singularities, Newtonian singularities. There's no reason why Newton shouldn't work. Afterwards, we learn that there's a limit of the validity of the theory when we know quantum effects, when we found out about H bar. Now we know about H bar, and we can put the same thing into GR and come up with a Planck scale at which we know that general relativity will not work. But between that scale and the scales that have been probed by our experiments, including gravitational waves, including the picture of the Event Horizon Telescope, there's a gap. There's a pretty substantial gap. And so there may still be a possibility for another theory to be working between GR and quantum gravity. So all the modifications that I will talk about here, they don't presume quantum gravity. They are modification to GR. They may become effective at the Planck scale or may become important at scale larger than the Planck scale. So we're talking about some modifications of GR that is not necessarily quantum gravity. Sorry for staying long on this, but it's a point that sometimes it's a little bit, and maybe I should have said all of this on this slide because there's a bunch of other possibilities here of other scales that may be introduced if you maybe consider lambda to be a fundamental constant and so on. And if you want to modify GR in some other way that is not necessarily a quantum theory of gravity. Maybe I will also give you this the PDF of the slides later on so that when you post this on YouTube, you can also put a link to the PDF if anybody wants to see them. So what GR tells us is that if a bunch of hypotheses hold, that is, general relativity works, matter satisfies the usual energy conditions, and the space-time is globally hyperbolic, and at some point trapped surfaces form, then singularities are inevitable. These are the singularity theorems that Penrose and Hawking and other developed in the late 60s and early 70s, and that granted the Nobel Prize to Penrose, which has an interesting story there. There's an interview on YouTube where Penrose says that he wished that he got the Nobel Prize for showing that singularities do form in relativity, and instead the official motivation was for showing that black holes are a robust prediction of general relativity, which is not exactly what the singularity theorems say. So I'm with Penrose, and I believe that proving that singularities inevitably occur in general relativity is interesting more than proving that black holes inevitably occur. Because if black holes are the only outcome, then we may be cut out from any theory of quantum gravity or any better theory of gravity beyond GR. On the other hand, if singularities are inevitable, but you have to modify the theory not to obtain singularities, and those are visible, then the thing is more interesting. So singularities, do we want them? Do we don't want them? There is also the point of view around that if singularities do occur and they're always behind horizons and they cannot communicate with the exterior, then there is no problem with GR whatsoever. So under that scenario, you don't have to worry about the fact that singularities cause pathologies that are way worse than the singularities that you have in electrodynamics, because they break the causal structure of the space-time, something that in Newton's theory or in Maxwell's theories does not happen. But if they're always hidden, then you don't have a problem. In order to have that, you need the cosmic censorship of Penrose, exactly, to be valid. Proving the cosmic censorship has been challenging, and there is no definite proof yet. And all the attempts in proving the cosmic censorship have basically focused on two sides. One is showing that you cannot overspin Kerr black hole in order to make it Kerr naked singularity. I'm fine with that, even though maybe I'm not sure what the state of the proof right there, but I'm fine with the idea that you cannot overspin a Kerr black hole. The other interesting aspect is singularities that form at the end of collapse. So when matter is collapsing, it forms a singularity that may or may not be naked, depending on the configuration, the initial configuration of matter. There are some counterexamples that are to cosmic censorship there that are a little bit contrived, that are not everybody agrees with, because they're simple toy models, there's no rotation, and there's simple matter models and so on. But they show that naked singularities can occur in that case. And to me, the appealing thing is it's nicer not to impose anything else on nature and have a scenario where nature itself tells us where we have to look for a better theory of gravity. So if those singularities at the end of collapse, they actually do occur, they're actually visible, that means that the effects of the modified theory of gravity, they can communicate with external observers, and we may, in principle, see those effects and get some data, experimental data, on a better theory of gravity. I'd rather have that and look for a better theory of gravity than a mechanism that hides that. We know that we have to modify GR, but we will have no way of seeing what's happening, and we will have no way of having the data to tell us how to modify GR. So from a point of view of a philosophical point of view, I'd rather go with not adding any extra layers to the theory to force singularities to always be hidden, because why should we? So how do you avoid singularities? You go back to the hypothesis of the singularity theorems, and you violate some of them. Keep global hyperbolicity. We keep the formation of trap surfaces because we're looking for formation of black holes and regular black holes. So we either have to modify GR, so corrections to general relativity, or violate the energy conditions, or both. A way to do that that unifies everything is to come up with some, what the people call semi-classical corrections, that basically all these modifications, you bring them on the right-hand side of the energy momentum tensor and consider that as an effective energy momentum tensor that gives you a matter source that is not physical. It contains both the physical matter source and the corrections to the energy momentum tensor and the corrections to the geometry, and treat that as your effective source and see what kind of collapse it gives you. Again, there's two places where you can look for singularities, cosmology and black holes. Most of my work has been in black holes, so I'm sticking with black holes right now. But in the future, I hope to spend a little more time on the singularities in cosmology. The issue is we have plenty of black hole candidates, but most likely there may be a horizon or other stuff preventing us from seeing what happens close to the singularity, while there is only one universe, and but the singularity in our universe is we may, in principle, figure out some geodesics that connect our telescope straight to that singularity, but there's a lot of stuff in between. There's a lot of matter, there's a lot of radiation, there's a lot of stuff in between, and so it's very difficult to extract a signal from experimental signal from very close to the singularity. So I'll stick with black hole, and my hope is that the modifications to the regime close to the singularity, modification to GR close to the singularity, they do propagate, they do cause some effects that can accumulate outside the horizon, and so that they may make something measurable. In the same way as the precession of the perihelion of Mercury, the scales of the orbit of Mercury are purely Newtonian. There's no need for GR there. But if you wait for 100 years, then the effects of GR accumulate enough that you have to take that into account. So something similar may be going on at the level of close to the horizon of black holes, and maybe in the near future, we may be able to actually measure departures from GR by measuring the cumulative effects, for example, of motion of stars around the supermassive black hole close to the Milky Way, or by measuring the with precision the accretion disks from the pictures of the Event Horizon Telescope. All right. Any questions, anything until here? Okay. So I hope people are still there. And now let's, yeah, Kostas, you were reassuring me that you're still there.
Yeah.
Okay, thanks. Well, one time I did actually a whole talk, and I was not in the meeting, and I realized only afterwards that there was nobody. So that happens. Okay, so now let's summarize a little bit dust collapse in general relativity. Non-rotating dust collapse, because I don't know how many students are here and how many people are very familiar with that, so I'll try to go a little bit quickly, and this may be more interesting for people that are not entirely familiar with the whole thing. But you probably know that we don't have an interior solution for KERR, and the moment you add rotation, even when you're considering collapse, the equations become a lot more complicated, so you don't have a dynamical scenario of formation of a KERR black hole analytical. Yeah, you have numerical simulations, but you don't have an analytical model that shows how to form a KERR black hole. We have instead analytical models of formation of the Schwarzschild black hole without angular momentum. And here we have the Penrose diagram, the maximally extended Penrose diagram of Schwarzschild black hole. And the exterior metric is given like this. I use capital letters for Schwarzschild coordinates. And the mass function m is here just a constant. That's the mass of the black hole. Yeah. So when you're thinking about collapse, you think about a spherical object that shrinks over time and undergoes collapse until it reaches a singularity, forms a horizon, and then the singularity. And so you can look at the particles at the boundary of the object from two perspectives. On one side, it's a particle in the energy momentum tensor that is collapsing together with the interior of the object. On the other side is a test particle in the Schwarzschild spacetime that is collapsing towards the center. The important assumption here is that the particle doesn't have to interact with the other particles. If the particle is not interacting with the rest of the interior, then it's following a geodesic. There's no effects of pressure. And so you can consider the motion of that particle both from the exterior side and from the interior side. So now let's first have a look at the exterior. This is the Schwarzschild metric. And I change coordinates and I go in what are called Lemaitre coordinates, which are essentially some kind of comoving coordinates. So now my time coordinates are called tau, my radial coordinates are called rho. And when I'm at rho constant, I'm sitting on a particle that is actually at a constant r, but moving radially towards the center. So it's collapsing radially. The radius of the collapsing sphere is given by this function capital R that previously was our Schwarzschild radial coordinate. That is now a function of rho and tau. So I take a particle located at rho constant, and I take R of rho naught as a function of tau, and I call it B naught of tau, and that's the radial trajectory of the infalling particle on the boundary. If I want a collapse model, the equation of motion looks like this. For the case in which this is, you see, it's a first order equation, so I already did one integration, and that means I had to set already one of the initial conditions, and that is the condition for the initial velocity, and I set that velocity to be 0 at infinity. And you can see it from here. If I take B naught to infinity, dB naught over d tau goes to 0. Yeah, that's what is called marginally bound. The particle that has 0 velocity at spatial infinity. Okay, so let's remember this equation of motion here because we'll see it later. And this is your picture of your collapse. We just looked at Lemaitre coordinates from the exterior, so test particle on the boundary. In general, you will have the whole interior matter that collapses at some point. So in the vertical axis, you have time. In the horizontal axis, you have a radial coordinate. At some point in time, the horizon forms, and then later on, the singularity forms. And at that point, you just have a Schwarzschild black hole. We take energy momentum tensor to be that of a perfect fluid, and we write the Einstein's equations for the interior. This is a bit of a mess, I know. There's lots of stuff. You don't have to look at all of this. On the left here, we have Einstein's equations. There's only 3 of them. Then we have definition of the Misner-Sharp mass, which is the amount of matter contained within a radius r at a time t. That's just a definition, so you have one extra function and one extra equation. Then you have conservation of energy momentum, or the Bianchi identities, that give you the equation for nu. We have 3 functions. Now this capital R is a function of small r and small t, which are the moving coordinates. Phi and nu are also functions of small r and small t. So these are your metric functions, 3 of them. And then you have your energy and pressure, epsilon and p, for your method. And then you can set up some scaling. So rescale capital R. Can you see my cursor if I move it on the over here? Can you see it? Or
Yes.
Okay, great. So you can rescale the radial function in terms of what is called the scale factor. That is just a high-dimensional quantity that tells you the rate of collapse. And you can rescale also the Misner-Sharp mass and the function phi. So then these are the field equations for collapse in general. You want to make things simple. The first example was what was done by Oppenheimer, Snyder, and Dutt in the 1930s. So you consider homogeneous dust. Dust means no pressure. So you set P equal to 0. Here it goes. Homogeneous means that the density is the same. It changes in time, but it doesn't change with radial coordinates. So rho epsilon is constant at any time slice, at any given t. When you take those assumptions, things simplify quite considerably. You get the equation from the Bianchi identity gives just nu prime equal 0, which gives you nu as a function of t. Prime means derivatives with respect to r, yes. Nu as a function of t, then you can rescale your time in order to set the nu equal to 0, so you get rid of that. And in order to have homogeneity, your Misner-Sharp mass becomes just R3 times a constant and not. Your metric becomes like that. Homogeneous, the density is a function of time only, not a function of r. Marginally bound, so you take your curvature k here to 0. That's what I got before. And dust, P is equal to 0. Dust is the requirement that the particles are not interacting with each other, and so they're following geodesics. So the particles on the boundary, they are described the same from the interior and the exterior. And the equation of motion that you get is this one, that, as you can see, is the same as the one before. If you don't remember the one before, this is A dot, so the A over dt is minus square root of m naught over A. M naught is a constant, A. Let's go back here. Minus square root of 2m is a constant over B naught, yeah? B naught now is A, small m naught is 2m, and the equation is exactly the same. The equation is actually a quadratic equation, so it's you have an equation for A dot square, you take the minus sign because you want to describe collapse. What you get is a simple solution for the scale factor that is this, that I believe everybody knows. At the time t equals 0, A is equal to 1, that's your initial time. At the time equal to 2 over 3 square root of m naught, you form a singularity. Interestingly, that in India obtained the same result before Oppenheimer-Snyder, so I am with my colleagues from India in pushing to call this Oppenheimer-Snyder dot collapse rather than only Oppenheimer-Snyder. The problem is that Dot died a few months after publishing this, and so the paper went unnoticed until some historians found it a few years ago. What happens to the formation of the horizon in this scenario? The horizon forms, so here I have the moving coordinates. The horizon forms first at the boundary and then propagates to the interior, and it reaches r equal to 0 at the same time at the formation of the singularity. The singularity is a space-like singularity, it's the Schwarzschild singularity. And you can see that here the apparent horizon curve, so you can set it as a curve as a function of t, is 1 over A dot, yeah? And the fact that it goes to 0 is because A dot, as A shrinks, as the size of the object that gets smaller and smaller, so A goes to 0, A dot goes to infinity, because if you remember the equation here, when A goes to 0, A dot goes to infinity, and as A dot goes to infinity, the apparent horizon goes to 0. That's what happens. And this forms a black hole. If you want something slightly more realistic, so you want maybe your collapse to slow down and your A dot to either stop or go to some finite value or so on, then the fact that the apparent horizon goes like 1 over A dot forces you to have a different behavior for the apparent horizon. So now imagine I build a model in which A dot goes to 0 instead of going to infinity. So it does collapse. Collapse goes, this A goes to 0, so we go towards 0, but we go to 0 slower and slower rather than faster and faster. What happens to the apparent horizon is that 1 over A dot has to go to infinity. But this is the apparent horizon only in the interior of the collapsing matter. So at some point, it has to pass the boundary. So you see that the apparent horizon crosses the boundary twice. Once when the horizon forms, and another time. And what happens there, it depends on what the exterior is. So this is the kind of modification that we are looking at. Something for which A dot goes to 0 rather than going to infinity, which is somewhat physically more interesting and realistic, hopefully. So now let's see how to get some models of, okay, again, questions, anything here? All good? All right. I hope all of these things are not too trivial, but I just like to keep it very broad. So now let's get to some models on how to get some regular black holes from collapse. The semi-classical cookbook is this. You get some modification of your energy momentum tensor or some modifications to your gravity, to your GR, and you put everything on the right-hand side and treat it as an effective energy momentum tensor. There's a big caveat here with asterisk. That is, we don't know if we even can do that. We are assuming that we can treat this modification in the strong curvature regime as an effective energy momentum tensor. It may be that whatever alternative theory of gravity you have doesn't allow you to do it at all. So this is a big question mark. And since we don't have a theory of quantum gravity, or we don't have any viable modification of GR that we know of at the moment, this is something that I have to put in the list of assumptions that I'm taking. Yeah. Because it's often, you hide it under the carpet, but it is there. So what you write is your Einstein's equations like down here. That is still Einstein's equations, but for an effective energy momentum tensor that takes into consideration modifications to T mu nu and modifications to G mu nu that may be averages of your quantum gravity or averages of your quantum effects on your matter. And the aim is to obtain a non-singular black hole, regular black hole. So something that has typically two horizons, an inner and outer horizon, and it looks like a black hole, and it is as small as modification from the previous Oppenheimer-Snyder dot scenario, as small modification as possible. So you want to tweak it as little as possible. You don't want to have 2 million extra parameters, because when you have too many parameters, then you can do anything you want, but you're not doing physics. So you want to add just a little tiny thing and see what that little tiny thing does it. And the goal is to achieve something that looks like a black hole, that has no singularity, and hopefully gives us some hint that how this can be observationally measured. Okay, so we can do it two ways. One way is we start from the exterior, the same as I mentioned before. We had Schwarzschild look at Lemaitre coordinates and get a trajectory of particle at the boundary there. So I know the exterior, I get the equation for collapse from the exterior, and then I infer what kind of interior I must get. Or I can do the opposite. I start from the interior, I get some assumption on my modification of my jar in the interior for the perfect fluid that is collapsing. And then from the modification of collapse in the interior, I infer the modifications to the exterior and the regular black hole. The first one, from the exterior, we do it in nonlinear electrodynamics. The second one, in the interior, we do it in this model from Asymptotically Safe. So before getting there, let's have a look at the general equations. So you have some action here, that is your usual GR, R, your matter, that is the Lagrangian for dust, and all the correction, you throw them in this Lagrangian correction, so that you get your effective energy momentum, that is going to be dust plus some corrections. In general, you can write your effective energy density as a series like that. So when epsilon is small, all of these extra terms are going to be negligible. But when epsilon becomes large, all of them one by one become somewhat important. If they're all independent, then you have too many parameters. What we want to have some kind of cutoff. We want to have a critical density. We want to have an energy density at which the modifications kick in, become important. So we want to control all of these alpha 1, alpha 2, etc., through only one parameter that I call epsilon critical. So this is a possible choice of effective energy density that is justified by what I'm going to obtain later. It's not the only possible one, but it's one that contains within itself several scenarios that have been looked in different models. If I take this choice for the effective energy density, then I'll get this modification for the equation of motion. And you can see when the A critical is equal to 0, then all of the stuff in parentheses becomes 1, and I retrieve my Oppenheimer-Snyder dot model. Interestingly, this exponent beta here must be set equal to 1 if I want to have quadratic terms in the effective energy density. So typically, this exponent here, we will not be able to play with it because I want to have terms in epsilon squared. That is going to be the next leading order terms. So that will set beta. We still have freedom to choose gamma, and still freedom to play with the critical, the acritical. As I said, several models are contained within this. The first and simplest thing you can think of is something that I did together with Leonardo Modesto and Cosimo Bambi when I was in Shanghai. That was this model of collapse inspired by loop quantum gravity, because in loop quantum gravity, they obtain an effective energy density in cosmology that looks exactly like this. So this 3m0 over a cube is epsilon. And so you have basically your effective epsilon is epsilon minus epsilon squared over epsilon critical. So you have only one term. Let me just go back here. You have only one term, the term in epsilon squared. So all alpha 2, alpha 3, they're all 0. And alpha 1 is minus 1 over epsilon critical. That is contained within here as well, because beta is equal to 1, gamma is equal to 1, and you have a minus sign here. So This is a bouncing model. Your collapse bounces. This is how you obtain your modified scale factor, but it's not a regular black hole. First of all, the Kretschmann scala diverges at r equal to 0, and the trajectories, infalling trajectories for the exterior of that spacetime reach a minimum size, and they bounce back. So it's not really something that you can obtain dynamically from collapse. Either if this happens, the whole cloud, the whole matter disperses, and you don't get any black hole in the end. So the loop quantum gravity bounds is contained within the formalism that I mentioned above, but it doesn't give you a regular black hole. So let's see at one where you can get a regular black hole. The action, now it's our GR, and some Lagrangian from nonlinear electrodynamics. The Lagrangian from nonlinear electrodynamics contains your Faraday tensor. There's an alpha that is just a coupling, and there's these two parameters, mu and nu, that are sort of free to choose in order for you to fix what kind of model you want. If you take mu equal -1 and nu equal 1, you obtain Reiser-Nordstrom. That's Maxwell's electrodynamics, and you obtain the Reiser-Nordstrom black hole, which is singular, so that's not what we want. So the one that I like, that everybody likes lately, is the Hayward black hole that is obtained for mu and nu equal to 3. So the mass function now, the line element looks the same as Schwarzschild, but the mass function is not a constant. It depends on R like this. And as you can see, there's one extra parameter that is this Q star, which is the magnetic charge of the nonlinear electrodynamics. For the black hole, it doesn't matter if it's an electric or a magnetic charge. For collapse, it has to be a magnetic charge, but let's not get into that. So as I said, we want to obtain collapse from the exterior. So the exterior is the Hayward black hole. Mu and nu are equal to 3. Your mass function is equal to this. Set Q star equal to 0, you retrieve Schwarzschild. Otherwise, for certain values of Q star, you have two horizons. One outer horizon that looks like the event horizon, and one inner horizon that looks like a Cauchy horizon. And the Kretschmann scala is finite at r equal to 0. You do the same, Lemaitre coordinates, the whole stuff from before, and you obtain this, which is, as you can see, a modification of the previous one that fits within the framework that I showed a moment ago for the effective energy density and for the scale factor. So this is the equation of motion obtained from the exterior. I take this equation of motion from the exterior and I plug it into my modification to Oppenheimer-Snyder to obtain an interior. This is now the equation of motion for A. And I can now relate my mu and nu for Hayward to my beta, which is equal to 1, as we said before, nu equal to 3, and gamma, which is minus mu over nu. So like this, I obtain the equation of motion for the interior of the modification of the Oppenheimer-Snyder dot collapse in the nonlinear electrodynamics. And this is the modification of the picture that I showed before. The interesting thing is that now the effective energy density has all the terms with alternating sign. So you have epsilon minus epsilon square over epsilon critical plus epsilon cube over epsilon critical square minus epsilon forward and so on and so forth. So you have a whole series. But since there is these powers, the series converges to this form of the effective energy density. And so the form of the modified equation of motion for the scale factor A dot is this. You can see if I set A critical to 0, that becomes again minus square root of m naught over A. So I retrieve again my Oppenheimer-Snyder. So this is the effective pressure that you obtain. And again, send epsilon critical to infinity, A critical to 0, epsilon critical to infinity. And you see that from here you obtain that P goes to 0 and you retrieve the Oppenheimer-Snyder. So now this modification is a perfect fluid. It's a modified dust scenario. So now you have an effective pressure. So the real pressure is 0, but the effective pressure is non-zero. And the pressure becomes 0 when epsilon is small, but becomes non-zero and negative when epsilon is large. Non-zero and negative because negative has this feature of producing these repulsive effects that slow down collapse. And A dot now goes to 0 as collapse progresses. As A goes to 0, the denominator here goes to a critical cube, which is finite, and a square goes to 0, so a dot goes to 0. So what you get is the dashed line in this plot here. So the thick line, the solid line, is Oppenheimer-Snyder dot, which collapses to a singularity in a finite amount of time. The dotted line is the loop quantum gravity model that I mentioned above, that bounces. And the dashed line down here is the Hayward modified collapse that produces a regular black hole. So the exterior is the regular black hole with two horizons, as I mentioned. And in the interior, you have that A goes to 0, so in an infinite amount of comoving time. So the singularity is sort of deferred to t equal plus infinity, and it never forms. And in the last few minutes, I will just mention this other model, this time obtained from the interior and obtained within asymptotic safety. Now here we did something slightly different. Our action is again GR plus a modification, but instead of adding the modification, we followed this very nice paper by Markov Mukhanov from the 80s, in which you just multiply your matter part of the Lagrangian by coupling that depends on the energy density. And you take, for a value of chi constant, you retrieve Einstein. And now we have to put the units in order to get G Newton, but that doesn't really matter. So for chi equal constant, you retrieve Einstein. Otherwise, for a varying chi, what you get is that your Einstein's equation, they look like this. You get your old energy momentum times some functions of the energy density, plus some other function of the energy density times G mu nu. So I can interpret the second term as an effective lambda, an effective, well, it's not a constant, a cosmological constant, but it's not a constant. And the first term as an effective gravitational coupling. So it's not Newton's constant, it's a variable variable gravitational coupling. And this is what makes your effective energy momentum tensor. So your T mu nu is your old energy momentum tensor from dust, while this whole thing here is your effective T mu nu. Now you have three functions there. You have chi, that is the coupling of your matter Lagrangian to gravity. G, your variable gravitational coupling, and lambda, your variable cosmological constant. You have to choose one, and once you choose one, the other two are fixed. We chose one from Bonanno's and Reuter work on asymptotic safety. So that is, you have an ultraviolet cutoff for GR, above which you have to introduce some modifications. And I'm not going into all the details of asymptotic safety because all of this looks exactly like the things we've seen before. This psi parameter here is basically our 1 over epsilon critical. And now from choosing G like this, we obtain chi and lambda, and that gives us our equation of motion in this form. Same as we said before, in the limit where our psi, I think this letter here is xi, in the limit when our xi is 0, so 1 over epsilon critical is going to infinity, in that limit, this whole thing reduces to Oppenheimer-Snyder. This is not so immediate to see. You have to do an expansion of the logarithm, but it works. So in that limit, you obtain Oppenheimer-Snyder. On the other hand, when you're not in that limit, A dot goes to 0, and A goes to 0 as t goes to infinity. Okay, there should be a plus here because this is a cosmology term. So we obtained, so here we obtained the equation of motion for the modified interior. And once we have that, and I will skip all the steps in between, you go back, Lemaitre coordinates, and retrieve your mass function for the exterior spacetime, and you obtain your regular black hole with your mass function that now looks like this. So this is a new kind of regular black hole that has a behavior similar to the Hayward black hole, but is a different thing that is obtained from the asymptotic safety. And down here, you can see the comparison of all the three. Now, the dotted line is the Oppenheimer-Snyder dot, it goes to 0 in a finite time. The dashed line is the one that I mentioned before with nonlinear electrodynamics, and the solid line is this one from asymptotic safety. So what did we get? We get a dynamical scenario of an interior matched continuously to an exterior in which matter collapses as the density becomes high enough. These corrections kick in and they slow down the collapse so that the scale factor goes to 0 in an infinite amount of time, and the a dot, the velocity of the scale factor, goes to 0 as well. That makes the apparent horizon reach a minimum value and turn back so that it crosses the boundary twice. At the first time, you have the formation of your outer horizon, which is the event horizon of your black hole and of your regular black hole. And the second time, you have the inner horizon or the Cauchy horizon, the same as in the Howard black hole, regular black hole model. And this is it. I think I went over time a little bit. So with this, I will stop. Thank you very much. And if you have any questions, feel free to ask.
Thank you very much, Daniele, for the very nice talk. Yeah, any questions?
I see one there. Another.
Yeah, Chayu.
Yep.
Yeah, I want to
these
ask,
are,
may I
go
ask
ahead.
one question? Well, actually, it's
Yeah.
not really a question. So, just like a clarification. So, in your loop quantum gravity approach, you simply replace the dynamical evolution of scale factor A by like some kind of analogy that you from what you have in loop quantum cosmology, right?
So yeah, you're talking about over here.
Yeah.
This one.
Yeah. The energy density.
Yeah.
So it's not really from a fundamental calculations of loop quantum gravity. Like usually people should start with Ashtekar variables and try to construct the effective Hamiltonian and
they did
corrections like that.
They did in cosmology. Ashtekar did it actually. Parampreet Singh and so on. You can find, and that's all pretty much complicated, all loop quantum gravity stuff. And in the end, they obtain this.
But and not in Oppenheimer-Snyder, no?
No, they didn't. In Oppenheimer-Snyder, that's what we did. We just closed our eyes and took their effective energy density and applied it to collapse. Yes.
Oh, okay.
And to me, it's fine even beyond loop quantum gravity, because what is this? It's your Oppenheimer-Snyder epsilon plus a term that goes like epsilon square that becomes important at some epsilon critical. So that's, if I want to do a Taylor expansion of my effective energy density at high densities, that's going to be the first term that I get, a term in epsilon square. So fair enough. They got it rigorously from the Mirzi parameter and Ashtekar variables and so on. They did all the stuff rigorously. And, they were way better than me at these things. And I just closed my eyes and took it and say, thank you, and plugged it in here. Okay. So that's how it is. But I like the fact that it's just a quadratic term in epsilon square. So that's what you reasonably expect to happen when you want corrections to kick in at some high densities. Yeah.
Sure. Thank you.
Yeah. Torben, I think, had a question. Torben had a question, I think.
Yeah, go ahead, Torben.
Well, actually, this was no thank you for the nice talk, but maybe I'm curious. I mean, since you know that I'm working on lensing, do you think one can probe something like this from the collapse by lensing as well? I guess it will be very difficult, but maybe some features could be different.
So there's okay. Ask me the question again. In the meantime, I think.
So basically, when we have the collapse, I mean, we have the Oppenheimer-Snyder model, and I think Volker, together with one of his master students, also investigated to some degree when you have a collapsing star, how the lensing features look like.
So, okay.
I suspect when you have maybe a slight modification, there might be very slightly tiny different features, which if you have good enough instrument, maybe you have some access to. Of course, this is very speculative now.
So no, yes. So there's two things here. if you did, okay, let's go slowly. Thinking about stellar collapse of massive stars, of course, they're opaque, so there's no light going through them. And so you can see lensing in the exterior. And that could be also after the black hole formed, you can have some tiny effects due to the fact that it's not exactly a Schwarzschild black hole. Mm-hmm. On the other hand, the light that is coming from the collapsing star may be affected by these modifications. So in that case, it's not exactly, you know, when you say lensing, I think about you have a source and you have light coming from behind the source, right? And that you can see it in the exterior. And what you're thinking about, I think, is light emitted from the source that is deflected by the massive source. In that sense, also, there could be some modifications, and I think some people like Nakao and so on have been looking at that. Then, yes, tell me. Yep.
Actually, I generally use the term of lensing not just by having somewhere a source behind which is then lensed by the object, but of course, light which is emitted by the object itself, and then it collapses to a black hole can theoretically also, if it's emitted in the right condition, lensed around the black hole maybe once and go to the observer. So that I personally would also call lensing in the end.
Yeah, I agree. And that would probably have some features. So this is what you were thinking about, right? Yeah. But that would have some features. And to investigate that analytically is not so obvious because if you look at just radial trajectories, you just get the redshift. And so you can do, you know, that is pretty simple. But if you want to see those features of lensed trajectories around the object as the object collapses, then you need to consider non-radial trajectories. And I think actually Volker Perlek is one of the experts on those things. One of the most, I would probably say the most expert person on these kind of things. So that's the person I would talk to if you want to look at that. But I'm pretty sure that it's not trivial, but I would agree that there should be some signals. There should be some differences.
Thanks. Anyone else? Yeah, I have a couple of questions. So one of them is related to collapse. The other one is about asymptotic safety. So yeah, about collapse. I mean, you studied this idealized, let's say, pressureless collapse. I mean, do you plan to? I mean, or do you have any idea how the more realistic scenario would look like?
I don't have any idea how the more realistic scenario would look like, and it's something that I would like to do very much, and it's something I've been thinking about and looking at for several years. The problem is analytical models for collapse. You have your interior, and now you're thinking your interior is a perfect fluid. Now it cannot be homogeneous anymore because you need to have matching. And so once you have pressures, the pressures have to be zero at the boundary. So now you have to have a density profile and the pressure profile that depend also on R in such a way that the boundary cannot be a constant comoving boundary anymore, but has to be given by the condition that P is equal to 0. And then you need to do the matching with the exterior, yes, and then solve the equations, the Einstein's equation for collapse. So the whole thing becomes pretty much a mess. The thing I've been thinking about and I've been looking at for a few years now is a perturbative approach. You want to make like the zero order is homogeneous collapse, and then you take a second order like in epsilon square and in p square that depends on and that depends on r square. Yeah. And so you make a perturbation of epsilon and a perturbation of p radial, yeah, and consider only the quadratic terms, for example. But then you plug that into the equations of the Einstein's equations, and even if you assume that epsilon 4, the terms in epsilon 4, the terms in epsilon 6, and all the higher order terms, and the same for p, they're all 0. That doesn't necessarily mean that for the other equations, for the Misner-Sharp mass and the other equations, all the terms will be 0. There will be terms that contain epsilon naught and epsilon 2, p naught and p2, 2 powers. And so you have a whole series of those And so you have to rewrite your Einstein's equations in terms of the series, make sure that they converge. And that's where I'm stuck.
Yeah.
So
Yeah,
I'm doing it, but it takes time. It would
Okay.
be nice if you could just cut the series, you know, at the I did a couple of works in the past.
I remember. Yeah,
Yeah.
I think we started doing that.
But the objection there is that you stop at the second order and you assume that all the other equations are negligible at higher order, which is not necessarily true.
Yeah, that's true. And about the asymptotic safety, I mean, you have this coupling to matter, the chi of epsilon.
Yeah.
I mean, if you think about cosmology, for example, I mean, why this chi function depends on an energy scale? Could it depend, I mean, on space-time, for example? I mean, could you have a varying chi, but as a space-time?
So actually, the nice thing about this action by Markov Mukhanov is application to cosmology, and that's the thing that I'm looking at, and I plan to look at for a while. And when you think about cosmology, you have the advantage that basically, as you go close to early universe, you can set one scale, and everything will depend on that one. Take the energy density, or take the size of the universe, or take the curvature. Doesn't matter. Everything is monotonic. So when you're setting your cutoff at critical density, that means a critical curvature. That means a critical time, and so on, and the critical size, and so on. So it doesn't matter which one you choose. Instead of chi of epsilon, take chi of Kretschmann scalar. Okay, that will imply all the others. Take chi of A, scale factors. That will imply all the others anyway. So pick one. And once the nice thing is that it depends only on one thing. So choose one thing to scale. It affects all the others. And then you just choose one parameter that is your cutoff. And that's the simplest modification that you can do to GR without introducing too many other stuff. And the nice thing about this one is that it automatically makes a variable G and a variable lambda. So that's a kind of appealing, because we see them kind of constant now, but like this, it was like, okay, that brings the question, can I have variable G and variable lambda in the early universe, but not free to choose as I want? I fix one thing, and then these are defined. These are
not only that, but also they don't have their own dynamics. I mean, they are fixed from the RG flow.
Yeah, exactly.
Yeah.
Okay.
Yeah, very good. I don't know. Is there any other question? Yeah, maybe we could stop the recording and continue informally if someone wants.
Maybe I can ask one more.
Sure.
Yeah.
Sure.
So, if I understand correctly, if you want to regularize the evolution of the scale factor, basically you have two options. Of course, it depends on the ansatz of the energy density. So the first one is that you have a scale factor going down and then approach to some constant or zero in asymptotic infinity, and the other one is that it bounced back, like what happened in loop quantum gravity, right? And and it seems that in your analysis, the first one is more successful than the other one. Would you like claim that in general the first one, the one that approaching to zero at the asymptotic infinity, is more robust, more generic, and in some sense more successful than the other one in this picture?
I like it more. I would not claim that it's more successful, or so there's first of all, just to mention something from before that, these are not the only possible scenarios. You also have the scenario in which the scale factor goes asymptotically to a finite value, not zero. Yeah. Okay. So in fact, I included it here. I never talk about it, but where is it? I included it here just because not to forget that it exists. Here, if I take the previous one, the case of with gamma equal to 2, which is not justified by any theory or anything, but if I just use it mathematically, that the scale factor goes to a constant value, to finite value, asymptotically. So a dot goes to 0, but a doesn't go to 0. So you also have that. And that's all the possibilities. So I like this one more because you get particles from outside can fall towards the black hole and not come out, and eventually asymptotically reach the singularity as t goes to infinity. While the loop quantum gravity model, you have this situation in which eventually something has to happen. If I go back to the loop quantum gravity, you have this critical time here in which essentially the whole star is not gravitating. Gravity is kind of turned off for a second, and then you have the time reversal in the expanding phase, but that has to turn into some kind of explosion. Yeah. And lots of people have been looking at this, and what kind of explosion would that be? And that it depends, because of course this is an idealized scenario. All the matter comes out at once, which is not realistic. If you want all the matter to come out gradually over a certain amount of time, of course, think about the star. For a star that collapsed, this whole process for moving observers happens in milliseconds. But for a distant observer, this could be millions of years. So you see a trapped surface here that lasts for millions of years, and so we think it's a black hole. And then you see a trapped surface here that lasts for millions of years, and so we still think it's a black hole. And if the matter comes out gradually, then okay, then there's a modification by which everything is ejected gradually, then we don't see anything. But if it's something similar to this, in which everything comes out at once, that's a huge explosion, and we should be seeing those. And we haven't seen, because these would be visible from very far in the universe. Maybe there is something like that, but we should be seeing those, and we don't. So for this reason, and for the fact that I like, let's go back to this. I like to keep all the terms in the expansion of the effective density, so that there is, alternating terms, and that's all of them. Mathematically, I think it's more neat to have that. On the other hand, the nonlinear electrodynamics theory that justifies this and the Hayward black holes are way less physics and way less solid and way less appealing than loop quantum gravity ideas. So if you're, from the point of view of the theory, you have an action of loop quantum gravity, it feels like more justifiable than a little bit of hand-wavy stuff that I've done in the things that I like more. So it depends on where you stand philosophically, right? If you're more a physicist, you may want a good theory, a solid theory, then you will go with loop quantum gravity, and you may like the bouncing scenario more. If you like the math more and you just look at the pleasing aesthetics of mathematics, then you want this whole series to converge, and then you may like my model more. But I don't see there is a reason to prefer one or the other intrinsically.
Yeah, excellent. Thank you very much.
Yep.
Thank you again. So I'll stop the recording.
Okay.